Okay, for introduction, we have objective and relevance. For the first objective, to explore how capacitor selection affects the performance of hand crank flashlights. The second objective is to investigate energy storage and efficiency improvements with different capacitor sizes. For the relevance, the first one is hand crank flashlights provide sustainable battery-free lighting solutions. For the second one, optimization ensures better performance, portability, and practicality. So how hand crank flashlight actually works? So we have the fundamental principle, which is converts mechanical energy into electrical energy through electromagnetic induction. So the step-by-step process is cranking the handle to generate mechanical kinetic energy. Electromagnetic induction, magnet moves through a coil of wire, creating a changing magnetic field. The third one is energy storage. Electrical energy is stored in a capacitor. And the fourth one is LED operation. Energy from the capacitor powers the LED. And we have the equation, which is Faraday's law of induction. Changing magnetic flux through a coil induce an electromotive force, which we call as EMF, producing current. So the key component in study prototype is actually the unipolar stepper motor, which is the generator, capacitors, which is energy storage, and LED, which is light output. So, what are the capacitor basics? So, what are capacitors? Devices that temporarily store and release electrical energy. So, I have put the picture over here, as you can see. And we have electrolytic capacitors used in the study, which our experiment used. It have polarized design, requires correct voltage polarity to function. For the structure, it have anode, aluminium or titanium foil with an oxide layer, which is dielectric. And we have cathode, electrolyte, solid or liquid, and conductive materials. For the capacitance formula, which is C equals to Q over V, or we can say as capacitance equal to charge stored over voltage across capacitor. For the performance insight, larger capacitance stores more charge and sustains higher current over time. For the study setup, we have an experiment objective, which is to compare the performance of a 47 microfarad capacitor and a 100 microfarad capacitor in a hand crank flashlight. And I have put these two, both picture of the both capacitor, as you can see, to differentiate it. It write as a 100 microfarad and a 47 microfarad to differentiate it. And we have evaluation matrix, which is about voltage output over time, current output over time, and also power output over 300 seconds of operation. And for the hypothesis, it is about higher capacitance. Capacitors will outperform smaller ones in energy storage and release efficiency.
So for the literature review, I will talk about the performance of the hand crank flashlights from other researchers' conception. So the hand crank flashlight is also known as a dynamo flashlight. It is an eco-friendly consumption since this flashlight does not rely on batteries, and it is very helpful in any emergency cases. The generator or dynamo, which transforms mechanical energy into electrical energy, is the essential part of this hand crank flashlight. According to W.A. Akpan and others, the mechanical energy conversion has roots in early human-powered devices like treadle systems and spinning wheels. As for the Andreas Landstorm and others explain that the human-powered devices work by applying mechanical force to drive a generator converting kinetic energy into electricity. Energy storage is a crucial for ensuring the flashlight can provide light without continuous cracking. As for A.E. Owo and others, discovered that the movement like cranking or pedaling generate rotational kinetic energy which powers the device. And in this study, we used these principles to develop a prototype with energy efficient design features.
The materials that we use for this project include one LED, two capacitor with a different value, which is a 47 microfarad capacitor, and a 100 microfarad capacitor, and lastly, a unipolar stepper motor. As for the apparatus, include a multimeter, which were used to test the voltage and current of the flashlight, a popsicle stick, which are used to build the hand crank of the flashlight, and a stopwatch that were used to record the time taken during flashlight was cracked. For the procedure, the first step is to connect the positive pin of the LED to pin 1 and the negative pin to pin 4 of the unipolar stepper motor. The second step is to connect the negative pin of the 47 microfarad capacitor to pin 2 and the positive pin to pin 3 of the unipolar stepper motor. The third step is to build the L-shaped hand crank or the handle of the flashlight using a popsicle stick and a glue gun. After that, the handle was then attached to the unipolar stepper motor using a glue gun. After the flashlight was fully constructed, it was then tested by rotating the handle of the flashlight to make sure it was fully functioning. For the fourth step, the flashlight was then connected to the multimeter to test the voltage of the flashlight. The fifth step, the hand crank of the flashlight was rotated and the result that was obtained from the multimeter was recorded. For the sixth step, the flashlight was connected to the multimeter again to test the current of the flashlight. And for the last step, the hand crank of the flashlight was rotated and the result that was obtained from the multimeter was recorded. The step involved testing the voltage and current will be repeated by replacing the 47 microfarad capacitor with a 100 microfarad capacitor.
in this study, we use an electrolytic capacitor to measure voltage, current, and power. So, as we can see, beside me is a graph figure, which is figure 1, voltage versus time. We can see that the blue one represents 47 microfarad capacitor, meanwhile the orange one represent the 100 microfarad capacitor. So we can see that this graph illustrates the relationship between the quickie duration and the voltage generated by the hand crank flashlight for both 47 microfarad and 100 microfarad capacitors. So the voltage increases over time for both capacitor, which is the 100 microfarad capacitor and 47 microfarad capacitor. So starting at the point 0.36 volts and reaching 0.51 volts at 300 seconds, the 100 microfarad capacitor outperforms the 47 microfarad capacitor, which starts at 0.27 volts and peaks at 0.34 volts. So the difference energy storage capacity due to the ability of the capacitor to have more energy storage. It could conclude in the formula, which is Q equals to C over V, which C represents the capacitance, while the V represents the voltage. The second one is figure 2, which is the current versus time graph. As you can see, like earlier graph, the blue line represents the 47 microfarad capacitor, meanwhile the orange line represents 100 microfarad capacitor. So, in this case, the current generated also increases over time with the 100 microfarad capacitor and displaying a steep rise from 4 milliampere to 32.2 milliampere at 300 seconds. So, in contrast, for the 47 microfarad capacitor, it exhibits a smaller and steady increase, which ranging from 2 milliampere to 4.3 milliampere. So, the difference highlights the superior energy management to the larger capacitor. So, according to the Faraday's law, which is have been explained in the slides. Um, the cranking motion induces an electromotive force, which is EMF, proportional to the rate of the change of the magnetic flux. So the higher capacitance enables the 100 microfarad capacitor to store and release larger currents over time, showcasing its efficiency in the energy conversion and storage. So the figure beside me is the figure 3, which is the power versus time graph, which the power output calculated with P equals to IV, which P represents power, I represents the current, meanwhile the V represents the voltage. This demonstrates a dramatic increase for the 100 microfarad capacitor starting from 1.44 milliwatt and reaching at the point 16.422 milliwatt at 300 seconds. So as for the 47 microfarad capacitor, on the other hand, it only peaks at just 1.462 milliwatt. As we can see, the larger the energy capacity of the 100 microfarad capacitor enables it to sustain higher power output, making it more sustainable for the prolonged lighting applications. For the last two graphs is figure 4 and figure 5, which is the current versus voltage. As you can see, the first one is the current versus voltage graph for 47 microfarad capacitor. Meanwhile, the other one is the current versus voltage graph for 100 microfarad capacitor. So these graphs show a relationship between current and voltage for the capacitors. For the 100 microfarad capacitor, which is in figure 5, the current increases almost linearly with the voltage in the range of 0.36 volt to 0.51 volts, which is reflecting its robust capacity to handle higher charge and discharge rate. In comparison, for the 47 microfarad, which is in figure 4, this displays more gradual increase with the diminishing growth at higher voltage. This behavior underscores the limited energy storage and transfer efficiency of the smaller capacitor, as its charge capacity is inherently constrained by the lower, by its lower capacitance.
So for the first study results for 47 microfarad, we have the performance summary, which is voltage and current outputs increased gradually but remain limited. When the peak power we have is 1.462 milliwatt at 300 seconds. For the observations, smaller capacitance results in lower energy storage capacity. Energy release was insufficient for higher sustained power outputs. And for the conclusion for 47 microfarad, is actually really unsuitable for applications requiring prolonged or intense energy output. So in real world, military or the high government use more farad, like 1000 microfarad, in their own flashlight to use it daily. For the study results for 100 microfarad, you have the performance summary, which is significantly higher voltage, current, and power outputs than 47 microfarad. We have peak power, which is 16.422 milliwatt at 300 seconds. And for the observations, the high capacitance allows for more charge, storage, and sustained energy release. And for the improved energy, management translates to higher efficiency and brightness in the LED. And for the conclusion, 400 microfarad is ideal for efficient energy storage and prolonged performance. And also, we have energy conversion and efficiency. For the energy conversion process, it has four processes, which is kinetic energy, cranking creates motion, which it turns into electrical energy. The generator converts motion into electricity, and then to energy storage, capacitor stores electrical energy, and finally to LED operation, which the capacitor releases stored energy to power the LED. For improving efficiency, the use of advanced electromechanical converters can enhance the energy transfer and storage. For example, systems designed to maximize the conversion of kinetic energy into electrical energy.
To conclude, a hand crank flashlight operates by using a generator to convert the mechanical energy from the rotating hand crank into electricity, which then power the light from the flashlight. In the analysis, we can summarize that having a larger capacitor will help in storing more charge, thus their ability to sustain a higher current and power output compared to a smaller capacitor that have a limit charge storage. This statement can be proven from the result where it shows that 100 microfarad capacitor have a greater voltage and current compared to the 47 microfarad capacitor, making the 100 microfarad capacitor more efficient in energy management. In summary, this study is focused on optimizing the design efficiency and usability of hand crank flashlight to enhance their performance and practicality. This device can be improved into sustainable lighting solutions by utilizing physics principles such as electromagnetic induction, energy conservation, and capacitance, increasing wider use and lowering reliance on throwaway batteries.